Hello students, welcome back. I hope you have revisited all the previous lectures of chemical kinetics. So today we are going to discuss in chemical kinetics the second order reaction, first order gaseous reaction and experimentally how order of reactions are found. Okay, so let's start with the lecture. Okay, so today we are going to discuss first order gaseous reaction. Okay, now just let us take some example to understand it. Now basically, what do we mean by a gaseous reaction? If the reactants are in gaseous state, then we will call it as a gaseous reaction, okay? Or simply we can also say that if in a reaction the reactant as well as product are in gases, so we can call them as a gaseous reaction. So let us consider a gaseous reaction something like this. Suppose we are having a hypothetical reaction in which A gas is changing into B gas and suppose C gas, okay. So this is just a hypothetical reaction, okay. So basically in the previous lecture we had covered first order kinetics, okay, in which we said that the product of rate constant into time is equal to 2.303 into log base 10 concentration of A at time t equals to 0 upon concentration of the reactant at time t. So this is what we basically derived in the previous lecture and we did some problem solving on this. Now if everything is in gaseous state, then how we approach this now? Because we know that for gases the main characteristics of gases is their partial pressure. So we have to express it in terms of partial pressure. Now we will assume that this is a first order reaction and all of them behave ideally. So we know that according to ideal gas equation PV is equals to nRT, right? So we can write N by V as RT by P. Now basically N by V is number of moles upon volume. So basically this is the concentration term, okay. So we will say that whenever we are writing in terms of concentration, we will say that concentration is also equal to RT upon P. Now we know that a reaction is carried out at a particular temperature and R is also a constant. So we will say that concentration is inversely proportional to the, okay, sorry, this expression here is incorrect. So let me write it again. So N by V will basically be N by V will basically be P upon RT, right? So we know that the concentration is equals to P upon RT. Now also we know that a reaction is carried out at a particular temperature. So temperature is constant in a reaction. So when temperature is constant, we know that R is also constant. So we can directly say that concentration is proportional to pressure. Okay, so we will express concentration in terms of pressure also, because we know that concentration is proportional to pressure. So what we are going to do over here, we are just going to put pressure instead of concentration, because concentration and pressure are directly related to each other. So this is what exactly we are going to do in today's lecture. We are going to solve some foundation level problem as well as higher level problem solving. So as I have already told you, in a gaseous reaction what I am saying is we have to express in terms of pressure. Okay, we have to express the first order kinetics in terms of pressure, because the partial pressure is the characteristics of a gas. When a reaction is happening, when a gaseous reactant is reacting, its partial pressure would decrease with respect to time. So in that case we don't know the concentration, so we will just say that the gases are behaving ideally and we know that the concentration is equal to P upon RT, and because the reaction is happening at a constant temperature, so basically concentration will be proportional to the pressure. So instead of concentration we will write the pressure. So the equation would transform into Kt equals to 2.303 log base 10 initial pressure, partial pressure of the reactant A at time t equals to 0 divided by the pressure, the partial pressure of the reactant A after time t. So our equation will transform into something like this. Okay, so I hope this is clear to everyone. You can just write it down. Okay, so let's start with a hypothetical reaction. Suppose again this reaction is following first order kinetics where A gas is changing into B gas plus C gas. Now let P naught be the initial pressure of A. So we are saying that when we are starting the reaction we are having only A, it will have some partial pressure. Now after some time T, when the reaction has occurred, some amount of this would have reacted, some amount of this would have formed. So that would correspond to some pressure, and these amount will also correspond to some pressure. The total pressure at that time T is Pt. Okay. So we are basically saying that at time T equals to 0, we are having only A gas, its partial pressure would be P naught, and at this point of time B and C are not formed, so they will not have any partial pressure. Now after some time T, suppose the reaction has occurred and some X moles have reacted. Okay. Now we can say that because PV is equals to nRT, a reaction is taking place in a container whose volume is fixed and at a particular temperature. Okay, so temperature is also constant. So we can directly say that number of moles is also proportional to the partial pressure. So suppose if in this reaction some amount of A has reacted. So obviously some moles have been reacted. So let us assume that its pressure changes by say X. Okay, so we will say that after some time some amount has reacted which corresponds to the X partial pressure. Okay, so X partial pressure of this has reacted. So after some time T, we will be left with P naught minus X. Okay, now 1 mole of this is forming 1 mole of B and 1 mole of C. So the X amount or the X pressure which has reacted of A will give us X pressure of B and X pressure of C. Okay, so I hope this equation is clear to everyone. We are just expressing the reaction in terms of pressure, right? So we will say that because it is a gaseous reaction, so we will assume that when X amount of this has reacted or some moles have been reacted, its partial pressure would decrease. So let that decrease in pressure be X. So X basically corresponds to the partial pressure of A which has reacted in the reaction. So we will be left with P naught minus X after time T, and X pressure B would exert and X pressure C would exert. Okay. Now we know that the total pressure, okay, the total pressure at time T will be equal to partial pressure of A plus partial pressure of B plus partial pressure of C, because after time T we are having all the three gaseous component in the container. So the total pressure exerted will be the sum of their partial pressure. So Pt will be Pa plus Pb plus Pc. Now we know that Pa is P naught minus X, Pb is X and Pc is also X. So basically we will be getting Pt as P naught plus X. So we can say that X is Pt minus P naught. Now remember, this data has been given to us that P naught is the initial pressure and Pt is the final total pressure. Okay, so just remember it is the total pressure, not the pressure of A. So basically we will get the expression for X. Now we know that the pressure of A after time T is P naught minus X. Okay, so pressure of A after time T is P naught minus X. So we will just substitute the value of X over here because X is unknown right now because we have been given only P naught and Pt. So we will put the value of X as Pt minus P naught. So we will get P naught minus Pt minus P naught. So this should come out to be 2 P naught minus Pt. Okay, so the pressure of A after time T would be 2 P naught minus Pt. Okay. Now we know that the initial concentration of A will be proportional to its initial partial pressure which has been given to us in the statement that it is P naught, and after time T the concentration of A would be proportional to the partial pressure of A after time T which is P naught minus X. So this is basically 2 P naught minus Pt. So we will directly say that because it is following a first order kinetics, so this will be Kt equals to 2.303 log base 10 A naught upon At. So we will directly use A naught as P naught and At as 2 P naught minus Pt. So we will get this expression. Okay. So when we express the first order kinetics of this reaction in terms of the partial pressure, P naught is the pressure at time t equals to 0, that is the initial pressure of A, and Pt is the total pressure when the reaction has occurred for time t. Okay. So I hope this expression is clear to you. You can write this. This is basically first order reaction. Okay. So just write this down. So basically whenever gaseous reactions have been given to you, we already know by the knowledge of stoichiometry that whenever gaseous reactions has given to us, we have to express everything in terms of pressure. So initial pressure is given to us at P naught. We'll say that when the reaction is happening, X is the extent of reaction defined per unit of pressure. So basically X pressure of this would have reacted. So we'll be left with P naught minus X, okay, and 1 mole of this is giving 1 mole of B and 1 mole of C. So the X pressure, which is corresponding to a certain amount, has reacted, then it would form the same amount of B and C. Okay. So just write it down. So basically in such questions, you might be given the value of P naught and Pt, okay, and time is given. So you can find out the rate constant for this particular reaction. Okay, you can write it down or can take a snapshot as well. Okay, so we are going to practice such kind of question because such kind of questions are very commonly asked in JEE, mains as well as advanced. Okay, so I hope everyone has written this. Okay, now let us take one more example. Suppose we have been given that, again this is a hypothetical reaction where A gas is changing into a B gas and C gas. Now let Pt be the initial, let Pt be the total pressure, this should be let Pt be the total pressure at time t. Okay. So let Pt be the total pressure of A at time t and P infinity be the total pressure at time t equals to infinity. So basically a data has been given to us. We have been given Pt, which is the total pressure at time t. Okay, so Pt is the total pressure at time t and P infinity is the total pressure at time t equals to infinity. Okay, now I will just explain why we are taking time t equals to infinity. So now let us assume that because initial pressure has not been given to us, right? We have been given Pt, which is the total pressure after time t. Okay, so Pt is the total pressure after time t. So let us assume that at time t equals to 0, we know that only A was present and that is corresponding to a pressure of P naught. Okay, after say some time t, when the reaction has occurred, the amount of A reacted is suppose some n moles, which corresponds to X pressure. Okay, so basically X pressure or X atm or X mm of Hg has reacted. So after time t we will be left with P naught minus X. Now 1 mole of this is forming 1 mole of B and 1 mole of C. So basically X pressure that reacted would form X pressure of BA and X pressure of C. Now what would happen at time t equals to infinity? Now we know that a first order reaction is never complete, right? We have already derived this in the previous lecture that At was equal to A naught into e raised to minus Kt. So we are saying that the decay of a reactant in a first order reaction is basically a exponential one. So basically the concentration of reactant is decreasing exponentially. Now because it is decreasing exponentially, so its concentration would fall to 0 at time t equals to infinity. So at time t equals to infinity, we will say that the reaction is complete. That means the complete reactant has reacted. Okay, so when complete reactant has reacted, this will become 0. Now we know that 1 mole of this is forming 1 mole of B and 1 mole of C. So the P naught amount would change into P naught of B and P naught of C. Okay, so I hope this step is clear to everyone, because at time t equals to infinity, the reaction has gone for completion. That means that the reactant has been consumed completely. So this has consumed completely. Okay, so we know that 1 mole of A gas forms 1 mole of B gas and 1 mole of C gas. So when the entire A has been exhausted, that means entire A has reacted. So the P naught pressure of A has reacted, so that would form P naught pressure of B and P naught pressure of C. Okay, so this we can write through our idea of stoichiometry. Okay, now we know that Pt, what is Pt? Pt was the total pressure after time t. Okay, so the total pressure after time t should be pressure due to A plus pressure due to partial pressure due to B plus partial pressure due to C, because after time t all the three gases are present, A, B, C all are present together. So after time t the total pressure would be corresponding to the sum of partial pressure of all the gases, which is PA plus PB plus PC. So PA is basically P naught minus X, PB is basically X, PC is basically X. So after time t we will get total pressure as P naught plus X. Now X is unknown over here, so we will say that X is PT minus P naught. Now P naught is also unknown to us in this particular reaction, because the data which has been given to us is the total pressure after time t and P infinity as pressure when the time was infinity. So P naught is also not known to us. So what we are going to do, we are going to calculate that P naught. So basically the pressure of A after time t, we know it is PO, P naught minus X. So X is basically PT minus P naught. Okay. So this would be 2 P naught minus PT. Okay. So I hope this is clear to everyone. If you have any issue in this, you can ask me. Okay. So basically we are carrying out the stoichiometric calculation, and we, after carrying the stoichiometric calculation, we understood that PA. Now what is PA? PA is the pressure after time t, which is corresponding to P naught minus X. So if we put the value of X, we will get 2 P naught minus PT. So now let us look at the time when it was infinity, that is when the reaction was complete. So we know that at infinite time, when the reaction is complete, the total pressure would be due to only B and C, because when the reaction is complete at time t equals to infinity, A has completely reacted, we are left only with B and C. So basically the pressure at that time would be partial pressure of B plus partial pressure of C, which is P naught. Okay. So this will correspond to the pressure, total pressure at that time, which is infinity over here, because P infinity is the time at time t equals to infinity. So P infinity would be P naught plus P naught. So we will say that P naught is equals to P infinity by 2. Okay. So we are going to just put the value of P naught over here. So we are going to get PA as P infinity minus PT. Now we know that the pressure of A after time t when the reaction has occurred is P infinity minus PT. Now we know the value of PT as well as P infinity. Now what we need to know is, we need to use the first order kinetics equation, because it is a first order reaction. So we will say that the product of rate constant into time will be equal to 2.303 into log base 10 concentration of A naught upon concentration of A at time t. Now we know that A naught would be proportional to the initial pressure. Now the initial pressure we know is P infinity by 2. We have calculated it that the initial pressure is P infinity by 2. Okay. And we know that the concentration after time t will be proportional to the pressure after time t. So pressure after time t for A is P naught minus X, which we have calculated as P infinity minus PT. So the equation would come out to be KT equals to 2.303 into log of P infinity upon 2P infinity minus PT. Okay. So this is the expression in terms of total pressure at time t equals to infinity and the total pressure after time t. Okay. So in this again the value of PT, P infinity might be given to you, time might be given to you. We can find out the value of K for this reaction. Okay. So just write it down. So here PT is the total pressure at time t and P infinity is the total pressure at time t equals to infinity. So we are assuming P naught to be the initial pressure, because initial pressure data has not been given to us. So we are assuming it to be P naught. Okay. And now we know that the reaction is happening. So let X be the pressure of A that has reacted per mole. So we left would be P naught minus X, B formed would be X, C formed would be X. At time t equals to infinity, we know that because it is a first order kinetics reaction, so at time t equals to infinity the reaction would be complete. So entire A would have reacted and it would have converted into B and C, because initially we took P naught as the initial pressure of A. So the amount or the pressure of B and C at time t equals to infinity would be P naught. Okay. So after time t we know that the total pressure is Pt. Okay, that has been given to us. Now the total pressure at time t will be equal to partial pressure of A plus partial pressure of B plus partial pressure of C, because all the three are gaseous component present at time t. So basically we are going to get the value of x as Pt minus P naught. We know that after time t the pressure of A is P naught minus x. We can put the value of x as Pt minus P naught. We'll get Pa as 2 P naught minus Pt. Okay. Now we know that at time t equals to infinity there are only two components B and C. So the total pressure at that point would be 2 P naught. Okay, so P infinity is 2 P naught. So P naught will be basically P infinity by 2. So we can put the value of P infinity over here, P naught over here as P infinity by 2. So we'll get Pa as P infinity minus Pt. Now we know that from the equation of first order kinetics that Kt is equals to 2.303 log of A naught upon At. So A naught will be proportional to the initial pressure of A and At will be proportional to the final pressure of A at time t. So basically A naught is proportional to P naught, At is proportional to P naught minus x, which is P infinity minus Pt. So we'll get this as the equation. Okay, so I hope this is clear to everyone. This is a very important question. Okay, we'll see how questions are framed on this as well. So I hope everyone has written this now. Okay, so let us take some more examples to understand this. Now suppose we have been given a reaction something like this. A gas is changing into say 2B gas and C gas. Okay. Now suppose in this there is a hypothetical question. Now suppose in this we have been given that let P naught be the initial total pressure. Okay, initial total pressure, that is at time t equals to 0. Initial total pressure means that at time t equals 0 only A will be present. So this is basically the partial pressure of A at time t equals to 0. Now suppose it has been given that Pt is the final total pressure at say some time t. Okay, so we have to write its first order kinetic equation in terms of pressure P naught and Pt. So just try to solve this. So we have been given at t equals to 0, this is P naught. Okay, this is P naught. Now suppose after time t some amount of it has reacted. Now because some amount has reacted, so its mole would be decreasing. Because mole is decreasing, so its pressure would also decrease, because moles is directly proportional to the pressure. So suppose that decrease in mole is reflected by x decrease in the pressure. So basically it will be P naught minus x. Now we know that 1 mole of this on reaction is forming 2 moles of B. So x pressure that has reacted would result in the formation of 2x pressure of B and x pressure of C. Okay, so the total pressure at time t would be due to the pressure of A plus pressure of B plus pressure of C, that would be P naught minus x plus 2x plus x. Okay, so this would be P naught plus 2x. So 2x would be equal to Pt minus P naught. So basically x in this case would be Pt minus P naught by 2. Okay, so we are basically interested in the initial concentration, which will be proportional to P naught, and the final concentration, okay, which will be proportional to P naught minus x. Now we know that P naught minus x can be written as x we know is Pt minus P naught by 2. So if you take this 2 over there, so we will be left with 3 P naught minus Pt upon 2. Okay, so At is proportional to P naught minus x, which is 3 P naught minus Pt by 2. Now we will directly write the equation Kt is equals to 2.303 log base 10 A naught was P naught, okay, and At is 3 P naught minus Pt by 2. We'll take this 2 in the numerator and we'll get 2.303 into log base 10 2 P naught upon 3 P naught minus Pt. Okay, so this is the equation. I hope this is clear to everyone. So just have a look how we are doing this. Okay, so we can change the different stoichiometry. We can write 3, we can write 4, 3b, 4b. So accordingly this will come at 3x, 4x. We'll calculate the total pressure. We'll get the value of x. So the pressure of A at time t would be P naught minus x. We'll put the value of x. We'll get the P At, okay, because At is proportional to Pt. So we'll just have the ratio and we'll calculate the K rate constant from the pressure data. Okay, so you can write this down or you can take a snapshot of this as well. Okay, similarly, if suppose at time t equals to infinity data has been given, so we'll say that at time t equals to infinity this has completely reacted. So we'll form 2 P naught over here because 1 mole of this gives 2 moles. So P naught would give 2 P naught and P naught or this. So we'll say that the pressure at infinity would be the partial pressure of B plus partial pressure of C, because at that time only B and C are present. So basically the pressure of B is 2 P naught and pressure of C is P naught. So this will be 3 P naught. So we can get the initial pressure in terms of the pressure, total pressure at infinity. So we can get P naught as P infinity by 3. So we can put instead of P naught P infinity by 3 and we'll get the expression. So that would be the expression in terms of total pressure at time t and total pressure at time t equals to infinity. Okay, so I hope this is clear to everyone and there is no doubt on this. Okay, now let us consider one more example. Now suppose we are having a reaction something like this. Suppose we are having 2A gas and suppose this is changing into B gas plus suppose 3C gas. Okay. Now let us assume that at time t equals to 0, the initial pressure of A was P naught. Okay. And suppose x is the extent of reaction in terms of pressure defined per mole. So x is the extent of reaction in terms of pressure defined per mole, because 2 moles of this is reacting. So basically 2x amount of this would have reacted, 2x amount or 2x pressure would have reacted. So the final pressure would be P naught minus 2x. So we know that from 2 moles of A we are getting 1 mole of B. So basically x moles of x pressure of B would be formed. Okay, 2x moles of A is giving B 1 mole of B. So 2x amount that is reacting would give x mole. Similarly 2 moles of A is reacting to give 3 moles of C. So basically 1 mole of A is giving 3 by 2 moles of C. Now 2x pressure has reacted. So 2x pressure would give 3 by 2 into 2x, that is 3x. Okay, so I hope this stoichiometric calculation is clear to you. This is the very basic. Okay, so we are basically saying that x is the extent of reaction in terms of pressure per mole, because the stoichiometry is 2. So the amount reacted in terms of pressure is 2x, right. So this leftover would be P naught minus 2x. Now we know that 2 moles of this is forming 1 mole of B. So basically 1 mole of A is forming half moles of B. So 2x which has reacted would form half into 2x moles or the pressure of B, which is x over here. Similarly 2 moles of A is forming 3 moles of C. So 1 mole of A would form 3 by 2 moles of C. Okay, so the 2x pressure has reacted. So 2x would react to give 3 by 2 into 2x pressure of C, that is 3x. Okay, So the pressure at time t would be, because all of them are gases, this would be partial pressure of A plus partial pressure of B plus partial pressure of C. So this would be basically P naught minus 2x plus x plus 3x. So this would be P naught plus 2x. So we can say that again x is equal to Pt minus P naught by 2. Okay, and we know that Kt is equals to 2.303 log of A naught. Log of A naught would be P naught, because A naught will be proportional to the initial pressure, and At would be proportional to P naught minus 2x. So basically we have to find P naught minus 2x. So x we know is Pt minus P naught upon 2. So when you take this, this will become 4 P naught, okay, minus 3 P naught minus 2 Pt upon 2. Okay, you just multiply 2 P naught minus 2 Pt plus 2 P naught. Okay, sorry, this will be 4 only. So basically we will be getting 2 P naught minus Pt in this case. Okay, so this 2 and 2 can also get cancelled. We will get 2 P naught minus Pt. So this is basically 2 P naught minus Pt. So we will use this expression over here. Okay. So I hope this expression is clear to you. Now suppose at time t equals to infinity, a data was given to us. So we know that at time t equals to infinity, this would have reacted completely. So basically 1 mole of this is, 2 moles of this is forming 1 mole. So basically P naught pressure would form P naught by 2. Okay, similarly 2 moles of this is forming 3 moles. So 1 mole of this would form 3 by 2 moles. So the P naught pressure that is reacting would give us 3 by 2 P naught. Okay, so basically at time t equals to infinity, the pressure, total pressure at infinity would correspond to the sum of partial pressure of B and C, because at time t equals to infinity only B and C are left, A is completely exhausted or reacted. So we will write this as P infinity as P naught by 2 plus 3 by 2 P naught. So P infinity will get this as, when you add this, we will get this as 2 P naught. So basically P naught would be equal to P infinity by 2. Okay, so we can put P naught as P infinity by 2. Okay, so we will get this expression in terms of pressure at infinity at time t equals to infinity and pressure at total pressure at time t. Okay, so depending upon what data has been given to you, if P naught Pt is given, we will use this. If P infinity and Pt is given, then probably we have to just express P naught in terms of P infinity. Okay, so just write it down. I hope these steps are clear to you. If anyone is having any doubt, just write in the chat box so that I can explain you. So basic numericals are formed in this portion, and like we have to do a lot of calculation. So these are frequently asked question in JEE that make us do a lot of calculation. So you have to ensure that you are calculating everything through your hand. Log values are typically given in your JEE papers, so you need not worry about the log. If you don't know, you can use your calculator then. Okay. So I hope everyone has written this and has come to this expression. Similarly, you can write expression in terms of P infinity and Pt. Okay. So let's start with some problem solving over here. So suppose the first question which has been given to us is something like this. Now this question says that the following data were obtained during the first order thermal decomposition of N2O5. So basically decomposition of N2O5 is given to us. 2N2O5 is reacting at this forming 2N2O4 and O2 gas. Now the pressure at time t equals to 0 is given as 0.5 and pressure after time 100 second is given as 0.512. Okay, so we have to find the rate constant for this reaction. Okay, so just try to solve it. I will tell you, take 2 or 3 minutes, write the equation. Okay. Okay, so I hope you have proceeded to the equation. So let us write this equation. So basically the reaction is 2N2O5 changing into 2N2O4 plus O2. Okay. So whenever reaction has been given to you, just ensure that the reaction is balanced, because that is one mistake that students make and they do not see whether the reactions are balanced or not. So this reaction is, as you can see, is balanced. So let us say that at time t equals to 0, the pressure was P naught. Okay, we know that the value of P naught is 0.5 over there. So we'll write in terms of unknown P naught Pt, and when we finally get the expression, we'll just substitute those values. Okay, so this is basically 0.512. Okay, so after say time t, we'll say that extent of reaction is x in terms of pressure defined per mole, because 2 moles of this is reacting, so this would lead to a decrease of pressure by 2x. So after time t, we would be left with P naught minus 2x. Now we know that 2 moles of this is forming 2 moles of N2O4. So 1 mole of N2O5 will be forming 1 mole of N2O4. So the 2x pressure which is reacting would form 2x pressure of N2O4. 2 moles of N2O5 on reaction is giving us 1 mole of O2. So we know that 1 mole of N2O5 on reaction would give half moles of O2, and we know that 2x pressure has reacted. So 2x pressure would give, 1 is giving half, so 2x would give x. Okay, so this is the partial pressures after time t. Now we know that the total pressure at time t would be due to pressure of N2O5 plus pressure of N2O4 plus pressure of O2. Okay, now we know that this is P naught minus 2x, N2O4 is 2x, and PO2 is x. So when we calculate this, this comes out to be P naught plus x. So basically PT is P naught plus x. So x in this case would be PT minus P naught. So the final pressure of A at time t would be P naught minus 2x. So we'll just write x as this. Okay, so we'll get PA as 3 P naught minus 2 PT. Okay, I hope this is clear to everyone. So the expression would be 2.303 into log base 10. A naught would correspond to P naught. So this is basically P naught, and AT would correspond to pressure of A at time t, that is 3 P naught minus 2 PT. Okay, this should be equals to K into T. Okay, so basically in this question, just you have to derive this formula. Okay, so we know the value of P naught as 0.5, PT we know, total pressure is given to us as 0.512, so we know the value of PT as well. Okay, we know the time because the time is at 100 second, so the time would be 100. So basically if you do the calculation, you can find out the value of K. Okay, so I hope you can do this from here now. So just look at the steps. I hope everyone is doing the same steps which I have been demonstrating over here. Okay, so just have a look at another question. So just solve this now. So this question basically says that there is a diethyl ether. Okay, so there is basically a dimethyl ether which is decomposing to give methane plus H2 plus CO. Okay, so this is also a balanced reaction because there are 6 hydrogen, total 6. There are 2 carbons, 1 oxygen. So this says that this is decomposing at 750 Kelvin. The rate constant of this reaction has been given to us as 6.72 into 10 raised to minus 3 per minute, starting with a pressure of 400 mm of Hg at this temperature in a closed container. How many minutes would it take for the pressure in the container to become 760? So basically P naught has been given to you because we know that starting with pressure has been written to you, that is the value corresponding to the pressure of pure dimethyl ether. Okay, how many minutes would it take to for the total pressure to become 760? Okay, so the total pressure has been given to us. Also you can see that initial pressure was 400. If reactant is reacting, its pressure is always decreasing. So if the pressure final is given as greater than that, that means that total pressure has been given to us. So in this question again, you have to just write the equation. Okay. So we know that at time t equals to 0, okay, I can also write 400 mm. Okay. Now after time t, we are assuming that x pressure is reacting. Okay. So because its stoichiometry is 1, so x pressure would have reacted in terms of mm now. Okay. So 1 mole of C2H6O is giving 1 mole of methane. So x pressure would give x pressure of methane. 1 mole of C2H6O is giving 1 mole of hydrogen and 1 mole of O2. So basically the x pressure would give x pressure of H2 and O2 as well. Okay. So we know that the total pressure after time t will be pressure due to C2H6O, because this is a gas, plus pressure due to methane, this is also a gas, plus pressure due to hydrogen, this is also a gas, plus pressure due to O2, that is also a gas. So basically total pressure after time t has been given to us at 760. So this will be 400 plus 2x. Okay, so we can calculate 2x as 360. So x would basically be 180 mm of Hg. Okay. So just one thing you should also remember over here is, sometimes in a chemical reaction one of the component given is solid. So while calculating the pressure, you don't have to take that solid component. So you have to keep this in mind. You don't have to just plainly do the same concept every time. You have to look the nature of the reactants as well. So basically we get the value of x as 180. Okay. So we know that Kt will be equal to 2.303 into log of base 10 A naught. Now A naught would be proportional to 400 divided by 80. 80 would be proportional to 400 minus x, which is 220. Okay. So from this we will get the value of T. K has been given to us as 6.72 into 10 raised to minus 3 into log of 40 by 22. Okay. So this you can calculate and we will get the time in minutes, because the rate constant is given per minute. Okay. So I hope this question is also clear to everyone. You can also do it by taking this as P naught, this as P naught minus x, 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 x. Same way you will land up in the same expression. Okay. So I hope this question is also clear to everyone now. So you can have a snapshot of the question, or you can write it down quickly. Okay. So I hope this question is clear to everyone now. So just solve another question. Okay. So this is basically saying that there is a sulfuryl chloride that is decomposing into SO2 gas and Cl2 gas. Again a balanced reaction. Time and pressure has been given to you. At time t equals to 0 we are having pressure of 180 torr. At time 240 second we are having the total pressure as 244, and at time 600 we are having a pressure of 302. So basically you have to prove that the reaction follows first order kinetics. So for proving the reaction that it is following a first order kinetics, we will assume it to be a first order kinetics, and using the expression we will calculate the value of K. Okay. So we will calculate the value of K at time t equals to 244 second, and we will calculate the time t equals to 240 second, and we will calculate the rate constant K at time t equals to 600. If it comes equal, if the rate constant is coming equal at different interval of time, using first order kinetics equation, it means that the reaction is following a first order kinetics. So just write the expression. Okay, so we are basically decomposing SO2Cl2 into SO2 and Cl2. So we know that at time t equals to 0, let the pressure be P naught. After say some time t, X has reacted. So the pressure left would be P naught minus X. X pressure of SO2 and X pressure of Cl2 would form. So the PT will be the total pressure, that is P naught minus X plus X plus X. So this is basically P naught plus X. Okay, so X would be PT minus P naught. Okay, so P naught minus X would become P naught minus PT minus P naught. So that would eventually add up. So the total pressure of SO2Cl2 would be 2 P naught minus PT. So the expression of KT would come out to be 2.303 log base 10. Initially it was P naught, okay, and the final it was 2 P naught minus PT. Okay, so this is the first order kinetics equation for this reaction in terms of initial pressure P naught and the final total pressure PT. Now at time t equals to 244, we can calculate the value of K. Okay, so when the time was 240 seconds, so this would be 2.303 upon 240 into log base 10. P naught was 180 and 2 P naught would be 360 minus 244, that is 116. Okay, so you can calculate the value of K at time 240 second. Similarly, we can also calculate the value of K at 600 seconds. So this would be 2.303, time was 600 into log base 10 upon initial was 180. So this is basically 180 divided by 2 P naught, that is 360 minus PT. So this is basically 58. So you can calculate the value of K at time t for 240 second and at time 600 second. Now if we do the calculation, the value of K would come out to be same in both the cases, indicating that this reaction is following the first order kinetics. Okay, so this is the way we prove that some reaction is following a first order kinetics. Okay, so we have to first use that equation and we have to see if that equation holds true, then the value of the rate constant at different time interval would come out to be same. Okay, so just have a look. You can take a snapshot of this as well. Okay, so I hope this is clear to everyone. Now just let us do one more question on this. Okay, so just solve this question. We'll discuss in 3-4 minutes. Just read the question and start solving it. Okay, so this reaction has been given to us as 2CO gas is changing into CO2 gas plus carbon solid. Now just see, here a solid has been given to you. Okay, so that would not be taken into the pressure. For pressure consideration, we have to take everything in gas because that is a solid, so we won't take it in the pressure consideration. Okay, so the total pressure at the end of 401 second with pure CO is found to be 0.313. At the time the reaction is 100% complete, the total pressure is found to be 0.1645 atm. Okay, so we have been given the total pressure after time 401 second. That means initial pressure of CO is not given to us. So let us assume at time t equals to 0, the initial pressure is P naught. Okay, after time 401 second, okay, suppose X amount of it in terms of pressure per mole has reacted. So basically the stoichiometry is 2. So 2x amount has reacted. So the pressure left would be P naught minus 2x. Now 2 moles of this is giving 1 mole of CO2. So 1 mole of CO would give half moles of CO2. So 2x pressure that is reacting would give us x pressure of CO2. Now this is solid, so we don't have to consider because solid don't exert any pressure. So the pressure after time 401 second would be P naught minus 2x plus x. So that would be P naught minus X. Okay, so I hope this is clear to you. Now, when the reaction is 100% complete, that means because it is following a first order kinetics, it means that the reaction will be complete only at time t equals to infinity. So, at time t equals to infinity, this would completely react. So, 2 moles of CO is forming 1 mole of CO2. So, 1 mole of CO would form half moles of CO2. So, the P naught pressure would form P naught by 2 pressure of CO2. Okay. So, total pressure at time t equals to infinity, that is when 100% complete, is P naught by 2. Now, we have been given that the value of P naught by 2 is 0.1645. So, P naught over here would be 0.3390, sorry, 0.3290. So, this would be 0.3290 atm. Okay. So, let us find the value of X now. Now, the PT has been given to us as 0.313. Okay. So, PT over here is 0.313. Now, this is equal to P naught, which is 0.329 minus X. So, X will get as 0.329 minus 0.313. Okay, this would be 0.016 atm. So, we will get the value of X, we get the value of P naught. Okay. So, we have to find the rate constant of the reaction. Now, because it is a first order kinetics, we will say that Kt is equals to 2.303 log of A. Now, A naught corresponds to P naught. So, the value of P naught is 0.329, okay, divided by pressure of CO at time t, which is P naught minus 2x. So, basically P naught minus 2x would be 0.329 minus, if you just do the calculation, so 2x would be this. Okay. So, this would be the value of rate constant. Okay. So, because we are doing it for 401 seconds, so just take t over here. So, we will get the value of rate constant per second. Okay. So, I hope this is clear to everyone. Okay. So, this is how you get the answer to the first question. So, I am not doing the calculation, I am leaving it to you because I want you to do these calculations which will help you in building the calculation skills. That is very useful for JEE. Okay. Now, the question says what will the pressure of CO after 401 second. Okay. So, the pressure of CO after 401 second is P naught minus 2x. So, the answer would be 0.329, which is P naught, which we have calculated, minus 2x, x we know is 0.016 into 2. Okay, that is this term only. Okay. So, this would be the pressure after time 401 second. Okay. So, I hope this is clear to everyone. Just have a quick look. So, these are actually a very good level JEE advanced level problems that are asked in JEE advanced. So, if you will see, there is a lot of conceptual approach. We are using stoichiometry, you are using chemical kinetics as well. So, basically this is a blend of 2 chapters. Stoichiometry is the very foundation. The basic stoichiometries will always be used in different chapters. Okay. So, just have a look. If you want to write the solution, you can write it or take a snapshot of this. Okay. So, let us do another question now, or rather let us do a concept first before we do the next problem solving. So, now let us discuss about second order kinetics. Okay. So, we know that, let us derive the complete integrated law for a second order kinetics also. Now, let us again assume that we are having a reaction A changing into B. Now, this is, let us say this is second order reaction. So, what we can say, is this a elementary reaction or a complex reaction? Obviously, it is a complex reaction because order is not matching the stoichiometry, that means it is not a elementary reaction. Okay. So, we will say that rate of this reaction is K into concentration of A raised to power 2. Okay. So we can write rate also as minus dC upon dt. Okay. So basically the concentration of A we are taking. So this should be equal to K into concentration of A raised to power 2. So this is the differential rate law. Okay, because this is the differential equation. Okay, so just now we have to carry out an integration to get the integrated rate law. Okay, so I will just bring the concentration term here and will take the dt over there. Now we know that at time t equals to 0, the initial concentration of A was A naught, and say after some time t, the final concentration of A is AT. Okay. So if you do an integration of 1 by A square, so this would come out to be minus 1 by A. Okay. So this is initial is A naught and final is AT. So this will be equal to K, and the integration of dt would be t. So the upper limit is t, lower limit is 0. So if you take this minus outside, so the minus minus gets converted into plus. So basically we will have 1 by AT minus 1 by A naught equals to KT. Okay, so this would be the integrated rate law for the second order reaction. So basically this is the integrated rate law. Okay. So AT is the final concentration of A after time t, A naught is the initial concentration of A at time t equals to 0. Okay. So basically we are using this, that integration of say x raised to power n is always x raised to power n plus 1 upon n plus 1. Okay, plus a c because it is a indefinite integral. This is a definite integral, so the constant term doesn't come in. So that is the basic of integration. Okay. So this can be written as a raised to a minus 2. So this is minus 2 plus 1 divided by minus 2 plus 1. So that's why a minus sign came over here. Okay. So this is a second order reaction with respect to a single reactant. Okay. So we can also have two reactants. Okay, something like this. Say A plus B is changing into C. Suppose this has been said to you as a second order reaction. So we'll say that rate of this reaction is K into concentration of A raised to power 1 into concentration of B raised to power 1. Okay. So for this also we can derive. So we'll just do the derivation for this as well. Okay, but mostly second order kinetics is not there in syllabus. We have to do zero order and first order. Small questions can come on zero order kinetics, that can be also done through the concept. So let at time t equals to 0, the initial amount of A is say A and the initial amount of B is B. After some time t, suppose x is the extent of reaction per mole. So x amount of this would react forming A minus x amount of this would react fall, and the remaining amount would be B minus x. So we can say that the rate law of this equation would be rate is equals to K into concentration of A raised to power 1 into B raised to power 1. So basically the rate can we write this as minus dA by dt. This is equals to K into A raised to power 1 B raised to power 1. Now for deriving the integrated rate law, we will write this in terms of x because we cannot integrate B with respect to A. Okay. So we will do is, what we will do is we will put A as A minus x. So this is basically A minus x, this is basically K into A minus x, and this is B will be B minus x. Okay. So this would come out to be dx upon dt equals to K into A minus X into B minus X. Okay. So this will be dx upon dt. So we'll integrate this from time t equals to 0 to time t equals to t. Okay. At time t equals to 0, the value of x would be 0, and after time t, the value of x is x. So this we have to integrate through integration by parts. Okay. So this is basically a minus x, b minus x equals to k dt. At time t equals to 0, the value of x is 0. After time t, it is x. So when you derive this, I think you can all do the integration. So we will get 2.303 log of b into a minus x upon a into b minus x. So this would be the equation of a second order kinetics if there are two reactants involved. Okay. So you can derive this through doing integration by parts. Okay. So I hope everyone knows the basic fundamental of integration by parts. Okay. So this is the expression which you are going to derive. So whenever you are having only one reactant, okay, only one type of reactant, then the expression would be 1 by AT minus 1 by A naught equals to KT. When you are having two different reactants, then the expression would come out to be 2.303 log of B into A minus X upon A into B minus X. Okay, so just write it down. Okay, so I hope everyone has written this. So now let us look at the characteristics of a second order kinetics. So the first thing which we should cover over here is unit of rate constant. Okay, so by just looking at the unit of rate constant, we can predict whether the reaction is a first order or a second order reaction. So we know that rate is equals to K into concentration of A raised power 2. The unit of rate constant is, the rate is mole per liter per second, and the unit of concentration is moles per liter square. So basically the unit of K would come out to be per mole liter second or per molar per second. Okay, so this you can easily do by dimension analysis. Okay, so the unit of rate constant is this. Okay, now let us look at some graphs. So basically we are having 1 by AT minus 1 by A naught equals to KT. Okay. So suppose we are plotting the graph of rate versus concentration. Okay, now we know that rate is equal to K into concentration of A raised power 2. So basically it will have a parabolic type of graph. Okay, so this would look something like this. Okay, it is maximum at the initial and it is decreasing. Okay, now if you plot one by A with time. Okay, so if you plot 1 by A with time, so basically 1 by A, so this is y, this is equal to m into x, and this is basically c. So basically this is y is equals to mx plus c form. So 1 by AT will be equal to KT plus 1 by A naught. Okay, so the intercept of this would be 1 by A naught and slope would be K. Okay, so the slope will be positive over here. So basically the graph would look something like this. This is the value of intercept, which is 1 by A naught, and the slope of this would be K. Okay. Now one important aspect which we wanted to derive is half-life time period. Okay, so this we have covered in the last lecture as well. So half-life time period or T half is the time when half of the reaction has occurred. That means the concentration of A after half-life would be A naught by 2, because half of the reactant has reacted, that means half is left over. So if you put AT as A naught by 2, so this will become 2 by A naught. So T half would come out to be 1 by K into A naught. Okay, so I hope this expression is also clear to you. And if we consider time of completion, okay, we have said that a first order reaction cannot go to completion as it requires time equals to infinity. But if we look for time of completion for a second order reaction, so when a reaction is complete, the value of AT becomes 0. So 1 by AT, because it becomes AT becomes 0. So 1 by 0 is infinity. So again, time of completion over here is infinity. Okay, I hope these are clear to you. So if you plot T half versus concentration, so if you plot T half versus concentration, so we know that the T half is inversely proportional to A naught. So this will be a rectangular hyperbola. Okay. So these are the few characteristics of a second order reaction. The unit of rate constant is per molar per second, and if we plot 1 by A versus T, so we will get a straight line with the intercept of 1 by A naught having a slope of K. If we calculate the half-life time period is the time when half of the reactant has reacted. When half of the reactant has reacted, that means the final concentration of A would be half, okay, because half has reacted, half would be left out. So A naught by 2 is the final concentration. So if you put AT as A naught by 2, so you get the T half as 1 by K into A naught. Okay. And if you look at time of completion, so time of completion is basically when the reaction is complete. Reaction is complete means that the final concentration of A is 0. So when you put AT as 0, so 1 by 0 is infinity. So time of completion is again infinity. That is a second order reaction does not go for completion. We assume it to be complete after infinite time. Okay. So you can just write it quickly now. Okay. So let us look at some examples of second order kinetics. The first example is, this we will also study in reaction mechanism, especially in the carboxylic acid portion, that is hydrolysis of an ester in alkaline medium. Okay. So whenever we are hydrolyzing any ester in alkaline medium, it will always follow a second order kinetics. Now this reaction is also called as saponification. So basic hydrolysis of ester is also called as saponification. Saponification is basically the formation of soap. Okay. So whenever you are taking a very big carbon chain group, so that is the sodium salt of the carboxylic acid containing a very big carbon chain is called as a soap. So if the R group over here, that is this methyl, instead of methyl is a very big alkyl group, so the product formed would be sodium salt of that alkyl group, which is also called as sodium salt of fatty acid. So basically that will be called as a soap. So when you hydrolyze the ester in basic medium, we will form sodium acetate and ethanol. So this is example of a second order kinetics. Decomposition of NO2, when NO2 decomposes into NO and O2, this is also an example of second order kinetics. Conversion of ozone into oxygen, 2 moles of ozone is getting converted into 3 moles of O2 at 100 degrees Celsius. This is called as this is example of a second order reaction. Similarly, reaction between persulfate and iodide. So persulfate is basically H2O2 negative. It is reacting with iodide to form sulfate and iodine. So this is also an example of a second order reaction. Okay. So these are the few example of second order reaction. Just write it down. Example of first order reaction. I hope you have memorized it till now. If not, then memorize it. There are few important examples that directly come in the exam. Similarly, examples of zero order reactions. Okay. So just write it down. So basically we have covered zero order, first order and a second order kinetics. Okay. Okay, so this is it for today. I hope like whatever we have done till now is very clear to you. So we started with a very important concept of first order gaseous reaction, and we did some problem solving on that, and then we switched on to a second order kinetics. We derived the second order kinetic equation in terms of one reactant as well as in terms of two reactants. Okay, then we did some properties or characteristics of a second order reaction, and then we did some examples of second order reaction. So today's daily practice problem sheet has been uploaded. You can download it, you can solve that as well. Okay, now if you have any doubts, you can just write in the chat box so that I can take those doubts. So I open this session for question and answer. Okay, so let's hope that you are posting your doubt, which I can address it now. Okay, there's a doubt by Mudapakka, which he says that in the last lecture I think you have said the average life is reciprocal of rate constant. Oh, is it so? No. Okay, so if I have said that, okay, just make a correction. So basically the average life is the reciprocal of half-life time period. Okay, so if that is the case, please make the correction. Okay, it might have slipped out of my tongue, so just make this correction. Okay, so there is no issue. Thank you very much Muddapakas for pointing this out, because many students might written as reciprocal of rate constant. Okay, so this is not rate constant, but this is the reciprocal of half-life time period. Okay, so which is 1.4 into k. Okay. So thank you a lot. Okay, so we need such kind of feedback because they are live lectures. So if any typing error or if any writing mistake has happened, we also should rectify it quickly. So thanks for pointing it out. Okay, sir, if molecularity is 3, can we say it as a complex? No, we cannot say. I have already said that if molecularity is greater than equal to 4, if molecularity is 4 or greater than equal to 4, molecularity greater than equal to 4 is not possible, because when the molecules are colliding together, the orientation of those colliding molecule would not be proper and the reaction would not result into. So basically molecularity 3 is possible, 4 is not possible. If any reaction is having a molecularity 4, or through stoichiometry we are saying that it is 4, that means it has to be a complex reaction. Okay, so if molecularity is 3, we cannot say it is complex. It can be complex, any reaction can be complex or elementary, but if it is an elementary reaction, okay, and the number of reactants are 3, okay, then it is not a complex reaction. Okay, so I hope I answered you correctly. Okay, can you explain hydrolysis of ester as a first order reaction? Rutik, I will explain this because this is basically the concept of a pseudo first order kinetics. Okay, so basically we say that the rate is equals to K into concentration of ester into concentration of water. Okay, now because water is an excess amount, so the concentration of water won't change much. So this is constant. Constant into another constant would be a constant. So we can write this as K dash into concentration of ester, where K dash is concentration of water into K. Okay, so this is first order with respect to ester, and such reactions which appear to be of second order kinetics but are behaving as a first order kinetics are called as pseudo first order kinetics reaction. Okay, pseudo means false, so this is not exactly a first order kinetics, it is a pseudo first order kinetics reaction, but we take it in the category of first order because it is first order with respect to ester. Okay, so we will get into pseudo first order reaction in the next class. So this doubt which you are facing over here will be cleared once we cover that portion. Okay, so is there any more doubt? Explain ions. Okay, oh, ions are nothing but they are charged species. Okay, so whenever an atom is losing electrons or gaining electron, it will form ions. Suppose an atom is gaining an electron, so it will become an ion. If it is losing electron, it will become a cation. So basically ions are charged species of an atom. They can be formed either by gaining of electron or losing of electron. Okay. So is there any more doubts now? So whatever doubts you have, if you think that some concepts that you have done is not clearly understood or you are facing some problem, then probably you can ask to us, you can write in the chat box so we can explain it back. Okay, so that is the one correction which everyone should make, which was wanted by one student, that average life is always the reciprocal of half-life time period and not rate constant. Okay, I think I mistakenly I have written rate constant, but it is the reciprocal of half-life time period. Okay, so I hope you are following the lecture sincerely and you are doing the solving as well for the topics that had been taught to you. Now after this class, that is the next class which will follow, will be basically experimental determination of rate laws, and we'll enter into some of the higher level concepts and higher level problem solving. Okay, so I hope you are enjoying, you are learning in a much easy manner, and you are having a very good clarity about the topic. So for any reading purpose, you can take up your NCERT and you can start reading it. For solving, just stick to the daily practice problem sheets now. Once we are done the core topics, the core theory of the chapter, then I can definitely recommend you some of the books which you can go and solve. Okay, so this is Animesh, your chemistry mentor, signing off for now. We'll catch you for some more interesting session in chemistry. Thank you, students.